started. As a sort of preliminary warning, the break may be a little bit after the halfway point today. So far we've been focusing on primarily on sum set problems. So A and B are just subsets of some additive group, and I'm interested in when their sum set is small. That's a kind of the heart of additive combinatorics, and we've seen a lot of nice combinatorial ideas to get an understanding of what happens in these cases. But there's sort of this very big world of lovely problems in additive combinatorics that are sort of stepping away from just the basic A plus B. And what I want to do today is give you a little flavor of that. So I'm going to do two sort of separate problems. They're each kind of self-contained, and they're sort of similar in that we'll be considering problems that look like this, but there are going to be some different features, some multiplications, some vector spaces. Another feature that's going to be new here is that, well, for the most part, everything you've seen me do so far it's been very kind of standard combinatorial reasoning. We do some uncrossing, we do some induction, we do some ball packing. Today there will be sort of a little bit more in the way of exotic ingredients, and that's particularly true in the first problem. So now I'm going to consider A as a subset of the real numbers, and well, I mean, that business that we said for the integers still works for the real numbers. If you wanted A plus A to be small, if you want A plus A to be very small, the way to do it would be to take an arithmetic progression or some generalization of that, or some similar rough set. Only now we're going to change things. Instead of just considering the sum set, I'll consider the product set as well. So this is what you think it is. I'm going to consider the product set, the set of all elements you can get by multiplying something in A with something else in A. And, well, maybe I should ask. So what would be a good way to make the product set very small? Yeah, I heard the right word there, right? A geometric progression would make the product set very small, right? I mean, that's the multiplicative analog of an arithmetic progression. If you take, you take any non-zero real number g, then g squared and g cubed and so on, then you'll get a nice little interval there. And if you multiply that by itself, it's basically going to double in size. So again, if we wanted this set to be very small, we'd take an arithmetic progression. If we wanted this set to be very small, we'd take a geometric progression. Those are two very different things. So the natural question that springs to mind is, could you choose a subset of reals for which both of these sets is somehow not too large? And a very famous conjecture of Erdős is that you cannot. So in fact, Erdős is going to conjecture that one of those two sets is extremely large, is in fact order almost a size of A squared. Right? So, of course, whenever you're taking this sum set, the maximum number of distinct elements you get can only be constant times, it can only be half A squared, right? And you can only, in a commutative group, you have this property that A plus B equals B plus A, but you can never get more than size of A squared elements in the sum set or the product set. And his conjecture is that one of them should have size close to that. So let me state this precisely. So for every epsilon greater than 0, every sufficiently large subset of reals it's going to have the property that the larger of the sum set and the product set is at least the size of A to the 2 minus epsilon. And so for every epsilon, however close you want to get to actually having size of A squared elements, if you look at large enough subsets of real numbers, either the sum set or the product set is going to be huge. Right, so I mean, it's really kind of back to this thing that there's no way of making them both small. I mean, the existing theory sort of tells you that if one of these sets were extremely small, then we could say what its structure is, and it would force the other one to be extremely large. But the middle ground in there is very, very foggy, and I don't think anybody hopes to have very good structure theorems. But nevertheless, I mean, we could hope for proofs of this that don't go through understanding the massive amount of the structure. And well, these boards are fun. Okay, so today, actually, let me put it over here since I'll write up the theorem, but we're going to take a sort of long detour before we get to the proof. So today's theorem is just a gorgeous one due to Elekes, which says that for every subset of reals, if you look at the size of the sum set times the size of the product set, that's going to be at least 1/64th times the size of the set to the 5/2 power. Okay. So in other words, the maximum of those has got to be at least constant times size of A to the 5/4. So which is still some distance from 2 minus epsilon, but it's something. I mean, it's something non-trivial. Let me just make sure I got that statement correct. Yeah.
So A times A can be how small? Smaller. Oh, it's the same. It's just you're still in a group, right?
That's right.
Same as your previous A.
Yeah. In fact, I mean, if you take this as that's right. You can take this as a geometric progression, and that minimizes the size of the product set.
So either of those could be linear.
That's right. Either one could be linear.
Right. Okay, I see. So this shows that you always have something.
That's right. So this is pushing things super linear. And already this is sort of well outside of the bounds of what anybody thinks we could get a really serious structure theorem for. So we're going to need some sort of different tool. We're not going to go through trying to figure out structure. I mean, in fact, I just love this theorem. It's so glorious. So we're going to take a kind of crazy detour that goes through drawing graphs in the plane, and then it goes through.
Crossing line.
Sorry?
Is it by crossing line?
Yes. Yeah. So we're going to draw graphs in the plane, and then we're going to prove a theorem due to Semeretti and Trotter concerning points and lines and their incidences in the plane, and then this is just going to drop out like magic. Okay, so it's and this is in part what I wanted to do here in this lecture was to show you that there are some kind of crazy tools that come to bear in this world, and there are some really, really lovely results. So this theorem of Elekes is particularly nice. I should apologize. I'm not particularly up to date on what the truth is. This has been improved. I'm pretty sure that Shoimoshi has the best known bound, and it's similar kind of trickery that results in it. Only it's different, and I have to admit that I don't quite remember what the best known thing is. I guess I can just look it up on the break. Anyway, so okay, as I say, so that's where we're headed, but the path is going to be anything but direct. So I'm going to think now about graphs. My graphs are going to be simple, so they don't have no loops and no parallel edges. And what I'm interested in doing is drawing them in the plane. And so for these purposes, I mean, your edges are allowed to be little curves. They aren't allowed to be crazy things. I mean, they say they're rectifiable. And the vertices will always be represented as points. Right, so an edge is going to be a curve that goes between its two endpoints. The edges aren't allowed to touch other vertices in their centers. What you are allowed to do now is have a crossing, though. So I'll permit you to draw two edges so that they cross. So we're not talking about embeddings. These are really some kind of drawing. But what I'm going to be interested in doing is counting this number of crossings. Okay, and so for my purposes, you could mean different things by this, but when I count a crossing, I'm just counting a pair of edges that intersect. Okay, so the crossing number of our graph G, this is the minimum number of edges of sort of pairs of edges, let's say. Which cross in any possible drawing. Right, so I don't know how good my picture is here. So here are the vertices. So here I've got a drawing of a graph in the plane, and you can see I have two crossings here. These edges, this pair of edges cross, and so does that. It looks like you could have done a little bit better, but whatever. Anyway, that's the notion of crossing number. And what I'm going to be interested in doing is getting some bound on crossing number. And there's there's kind of an easy one that we can get from Euler's formula. And I'm just going to write down this as, I'll say corollary here, although I haven't written the theorem. Euler's formula tells you that a planar graph can't have too many edges. Right, so if you have a graph that you can actually embed in the plane without too many crossings, then it won't have too many edges. And I'm going to write this, well, so if the crossing number of your graph is 0, that means it can actually be embedded in the plane, then the number of edges is always going to be at most 3 times the number of vertices. Maybe I'll just sort of say out loud where it comes from, but I won't step through the details. So what you'll know is the number of vertices minus the number of edges plus the number of faces is equal to 2. So that tells you that this quantity, in fact, and all we care is that this is at least 0. And now what happens here is when you look at the boundaries of the faces, right, if you count up over all the faces the length of its boundary, that's got to be 3 each time. Or sorry, it's got to be at least 3 each time. And that double counts the edges. So 3 times the number of faces must, so twice the number of edges must be at least 3 times the number of faces. And when you plug that in, this thing is dropping out. Okay, so Euler's formula tells us that planar graphs can't have too many edges. Now, this fact we can use to get a good estimate on crossing number when you're looking at graphs with not too many more edges than a planar graph could have. Okay, so let me write down as an observation here. So my observation is going to be that the crossing number of a graph G is always at least the number of edges minus 3 times the number of vertices. And what we're going to do is fairly simple here. So let's take okay. So let's start with the best drawing you can find of your graph G. So consider a drawing with crossing number C. Consider the best drawing you can find. It's got crossing number C. And now what I'm going to do is I'm going to modify the graph in the following manner. Anytime you see 2 edges that cross, I'm just going to delete one of those 2 edges. Okay, so we're going to form a new graph, G prime. G prime is going to have the same set of vertices but somewhat fewer edges by this process. So just any time you see 2 edges which cross, you chuck one. So the good news, of course, is now that G prime is actually going to be a planar graph, right? I mean, the drawing that you started with had possibly many crossings, but we've chucked one edge. I mean, anytime we saw 2 edges which cross, we deleted one. So we're down to a picture that has no more crossings. So G prime is planar. Right, so that tells me that the number of edges in this smaller graph, E prime, this is at most 3 times the number of vertices. But how big is E prime? Well, we started with E edges, and we deleted one for each crossing. So we started with E edges, and we removed one for each crossing. Now, I seem to be suggesting this. In fact, you might have removed the same one twice. So we might get this. But the number of, so this number of edges we have will be at least the number of edges you started with minus the number of crossings. Right? And good news, that gets us the bound, right? So rearranging, that just gets us this. So this is nothing fancy at all, right? This is just Euler's formula and very sort of simple, naive thing, right? If you have a graph drawn on a plane and you'd like to reduce the number of crossings, well, you can throw away an edge and get rid of one crossing. And that's all we've done so far. And this bound, well, as I say, it's fairly good if the number of edges in your graph is close to the number that a planar graph would have. If your number of edges is around 3 times the number of vertices or a little bit more, this is a pretty good estimate. I mean, we could even sharpen this up a little bit and it would even be tight. But it's a terrible estimate for graphs that have lots of edges. So if you think about what this would say if your graph was like the complete graph on n vertices, this is going to tell you that the complete graph on n vertices, well, there the number of edges is like half n squared, and the number of vertices is n. So it's going to tell you that however you draw the complete graph on n vertices, you see about n squared, half n squared crossings. But in fact, but in fact there are many, many, many more crossings. Any drawing of the complete graph Kn has constant times n to the fourth crossings. So this is way off for graphs that are dense. And there's a really lovely theorem. This is the crossing lemma. That gets us a much better bound. And this is the following. So now I need to assume that the number of edges is not too close to this low side. I'm going to need the number of edges to be at least 4 times the number of vertices. Then what's true is the crossing number of G is at least the number of edges cubed divided by 64 times the number of vertices squared. Right, so if you think about complete graph on n vertices, this is now, you've got half n squared is your e, so you've got n to the 6th in the numerator and n squared in the denominator. So this is getting you constant times n to the 4th. Right? So it's telling you, however you go to draw the complete graph on n vertices, a constant fraction of all pairs of edges will cross. So this lemma is, it's particularly significant in the in this world of graph theory where you're interested in drawing planar graphs. It also has a really glorious proof. So the idea of the proof is it's kind of very simple. So we have an estimate that we have a sort of bound on crossing number that works really well when you have a graph that's not too dense. Right? So we have a good estimate for graphs that are sparse. It's terrible at this high end. What we're going to do is we're going to take advantage of this by sampling our graph. So what we're going to do is we're going to take our graph, instead of trying to just apply this observation at the start, we're going to sample it by picking up a subset of the graph to get us something that's more sparse. And then the power of this at that sparse level will apply to give us something strong, which is going to lift up to our general estimate. Right? So it's it's a really nice trick. So again, you sort of have an estimate that works well in the sparse case. You'd like to deduce something in the dense case from it, and you do it just by sampling so that you pick up something sparse. So let's go. So let's fix a particular drawing of our graph. So let's I'm going to have to throw these v's and e's around a bit. So let's declare little v and little e to be the number of vertices and edges. And let's say c is the crossing number. Which was lowercase before. So c is the crossing number. And let's just fix some best possible drawing of g. So let's fix a drawing with crossing number c. Okay, so as I promised, we're now going to be sampling. So I'm going to be choosing a subgraph of this, and here's how I'm going to do it. Well, I'm going to be picking up a subset of vertices by taking each vertex independently at random with probability p. And let me tell you what p is. So I'm going to let p equal e divided by 4 times v. Sorry, I want that the other way around. 4v divided by e. So the good thing here is we've arranged that e is at least 4 times v, so this is less than or equal to 1. It's not fair to choose things with probability bigger than 1. So that's going to be my probability, and I'm going to choose a subset of V, of our vertex set, by selecting each vertex independently at random with probability P. Okay, so I've chosen a random subset of vertices. That's going to give me some edges. I'm going to take all of the edges that you get, which have both ends in V prime. So I'm going to define E prime to be the set of all edges in my graph, such that both U and V were selected in V prime. So that gives me a graph, G prime equals V prime E prime. And this we would say is an induced subgraph of your original graph. Right? We selected some subset of vertices and all edges between them. Right. Okay. But so we've picked out a subgraph G prime, but our subgraph also it has a natural drawing, right? We started with this initial drawing of the whole graph. We get a drawing of G prime, but just throwing out the parts we don't have, right? So let me just say G prime inherits a drawing from G. And I'm going to let C prime be the crossing number of this drawing. So C prime is the number of crossings in this drawing. Okay. So again, we started with our big graph. We've kind of selected this subgraph. And our subgraph is now going to be a sparser graph. And because of that, this estimate that we have is going to be a good one for our subgraph. So let me just write down what this estimate says. So this estimate is telling us that the crossing number, I mean, this is always true, but in particular for this graph, we have the crossing number is at least the number of edges minus 3 times the number of vertices. And actually, maybe, let me just go ahead and rearrange this. So let me write this as 0 is less than or equal to the crossing number minus the number of edges plus 3 times the number of vertices. Right? So that's true automatically. That's just this observation. But actually, if I want to think about this as a probabilistic process, C prime and E prime and V prime, they're all random variables. Right? I mean, this identity, which is true every single time, must also be true in expected value. Right? I mean, this is true every time, but it's also true in expected value. And the nice thing about the nice thing about these expected values is that I can compute them very easily. Right? What's the expected value of V prime? Well, V prime is just the number of vertices we picked up. We picked up each vertex with probability P, totally independent. So the expected value of V prime is going to be exactly P times V, number of vertices we had originally. Right? So I mean, each vertex gets picked up independently with probability P. The number of vertices you expect to get is P times the total. How about edges? Well, what's the probability you pick up an edge? Well, in order to pick up this edge, you have to pick up the vertex U and the vertex V. right? Those are independent events, each with probability p. So the probability a given edge gets selected is p squared. So if the probability that each edge gets selected individually is p squared, the expected number of edges we pick up is p squared times the number of original edges, which is p squared e. How about a crossing? Oh, yeah, I maybe should have made clear that you don't need edges. Edges that share a vertex need not cross. If you have two edges that share a vertex, there's no point in having them cross. I could have rerouted them like this. So if you've taken an optimal drawing, you won't have adjacent edges crossing. So if you have a pair of edges that cross, they will in fact look like this. And then what's the probability that that crossing survives in our subgraph? Well, in order for this crossing to survive, you have to select all 4 of these vertices. Right? So the probability this particular crossing still appears in our new drawing is p to the 4th. And therefore, the expected number of crossings in our drawing is p to the 4th times the number of crossings of the original graph. So now let's just compute. So now I need to figure out what p was again. P was 4v over e. So plugging in 4v over e down here gets me an e cubed over 16v squared. And plugging in 4v over e here gets me a 64v cubed e cubed. And I can cancel one of those factors of v. And now I've just got c minus e cubed over 64v squared. And that's what I want to prove. So now that tells me that c has to be at least e cubed over 64v squared. And that's what I was trying to show you to begin with. Right? So that's the proof. So it's it's a really lovely, it's a really, really beautiful argument. It's so clean, and the idea behind it is actually simple enough, right? I mean, you basically have a circumstance where you have an estimate which works well in a sparse case, and you want to apply it in a meaningful way for a denser graph. And what you've done is you've kind of sampled that denser graph and then just applied it on the sample, and and that's it. Okay, so that's the crossing lemma. All right, so the next thing we're going to do is jump to a problem in combinatorial geometry. And this is a theorem of Semmereti and Trotter. And they were interested in the following. So they're interested in looking at configurations of points and lines in the plane, right? So you have some distinguished set of points and some distinguished set of lines. And the question that they're going to answer is just how many pairwise point line incidences can you possibly see? Right? So I'm talking about a set of vertices and a set of lines. You're not allowed to pick the same line twice, right? So I mean, you could decide to put all your vertices on a line, and that would give, many incidences between this line and those. Oh, I'm going to say vertices instead of points half the time. So, any rate. So yeah, a vertex set for me is a point set in the plane. I'm ignoring the difference. So if you want a set of points and a set of lines with many kind of pairwise incidences, I mean, so you could put one line down and put a whole bunch of points on it, but that's actually a bad start. I mean, that gets you a good number here, but the rest of the lines will be able to take at most one. So that's a bad idea. A grid would have been better, and you can do better yet. In fact, their theorem gives basically a best possible bound up to the constants. And okay, so let me write it. So let's so I'm going to let V be a set of points. L a set of lines. These are both in R2. And let me just declare, this was a bad choice of letter. Well, it won't matter. So Q is going to be the number of incident pairs. So this is the number of pairs, say PL such that P lies on the line L. Right, so Q is just that number of incidences, number of point line incidences. Then what's true is, and I'm going to write a constant here. It's by no means the best constant, but it's what'll easily drop out of our argument. Q is at most 4 times the number of points to the 2/3 times the number of lines to the 2/3 plus the number of points plus the number of lines. Right, so this is a significant theorem from the combinatorial geometry perspective, and the original proof was considerably more difficult than the one I'm going to show you now. As I say, it's essentially best possible. Yeah, let me do this. Let me put up the statement of the crossing lemma and erase these couple. Okay. So this is our crossing. Sorry. Now what we're going to do is we're going to lean on the crossing lemma to prove this thing, right? So what we're going to do is kind of take this point line configuration and make a graph, really in the most obvious way possible. I mean, in exactly the way you would think of making a graph. Let me maybe note at the start, I can assume that every line contains at least one point, because otherwise throwing it out would only improve the bound. So let me just say, we may assume every line contains at least one point. Okay, and now I'm going to construct a graph. Now, let's draw a picture. So I've got I've got some set of points here and some set of lines, right? I mean, it should be clear, but let me just say it for emphasis. Of course, it does not have to be the case that any time two of my lines cross, that crossing point has to be a point in your point set, right? You get to select whichever set of points V you like. I mean, if you want, you can select a silly point out here that's only on one line. You're allowed to do whatever you want. But, I mean, so you select any set of points and any set of lines, and then, the claim is that this is going to hold. Now, what we're going to do is we're going to prove this by constructing a graph. And we're going to, as I say, we're going to do this in the most obvious way possible. Well, I mean, I'm leading the witness here a little bit. V is my set of points. V is also going to be the set of vertices. That's not an accident. So this is going to be the vertex set of the graph. Now what I'm going to do is anytime you see a line here, and you look at two consecutive points in my set V, which lie on that line, I'm going to consider this line segment in between them as an edge. Right? So for each line in L, so it's going to look like this. You have point 1, and then point 2, then point 3, and so on out to point K here. So for each line in L, I'm going to add an edge between any two points that are consecutive on this line, and I'm going to go ahead and draw that edge in the plane as a straight line segment. So we add a straight edge between each consecutive pair of points on this line. Let me say for each line L in L, we're going to add a straight line between each consecutive pair of points that lie on this line L, right? So in this case, in this case, what's happening, I have K points from my point set that are lying on this line. That's going to give me an edge here, an edge here, an edge here, all the way up to an edge here. So I'm going to get K minus 1 edges. So this gives K minus 1 edges for a line with K points. Right, so all told, what's my number of edges? So the number of edges in my graph, I can get this by summing over all the lines of the, let me start to say it in words, the number of points on L minus 1. Right, but if you sum up over all lines the number of points on the line, that's just giving you Q, right? That's just one of the many ways, or maybe one of the two obvious ways to count Q, the number of pairs of point line incidences. So this first quantity summed over all the lines just gives me Q. So this is exactly equal to Q minus my number of lines. Right, so now I'm perfectly primed to apply the crossing lemma. I've got a lovely graph drawn in the plane. As you can see, it's not embedded in the plane, right? So if you've got, would have been better if I'd drawn a little bit more of this perhaps, but so in this case, if this was my graph, I would have an edge between these two vertices and an edge between those two vertices, which are then going to cross. All right, so we've got this nice kind of graph drawn in the plane. It will be drawn with crossings, but I have a good bound on the total number of crossings you can have. What's a good bound? How many crossings could I possibly have? I claim that the number of crossings is at most size of L squared. right? I mean, two lines can intersect only once. I mean, actually, you could probably say something like size of L choose 2 if you wanted to, but I'm going to be pretty cavalier with the constants. Really the only reason I'm keeping the 4 there is because it comes out easily. You could really do better. So anyway, so the number of lines squared, that's at least the number of crossings. And that's going to allow us to apply the crossing lemma. Oh, but I'd first better check. If the number of edges is less than 4 times the number of vertices, then that lemma doesn't apply. So let's check what happens there. So first, if the number of edges, so the number of edges is q minus size of L. If that's less than the number of vertices, well then, what's true? Then q is going to be less than or equal to size of v. Oh, what am I saying? There's a 4 here. Sorry. Sorry. If my number of edges, which is equal to this, is strictly less than 4 times the number of vertices, then q is going to be less than 4 times the size of v plus the size of L, which is less than what I'm aiming for, right? Right, we've got a 4 times size of v plus L here, and we're okay. So in that realm where the crossing lemma would not apply, my bound holds very easily. So that allows me to apply the crossing lemma. And that tells me that this number of crossings in my graph is going to be at least the number of edges cubed, which is q minus the size of L, divided by 64 times the number of vertices squared. And that's all good. Right. So and now I'll just swing things around. So I can bring the 64 v squared L squared. So I get 64 size of v squared size of L squared. That's at least q minus the size of L cubed. And now I'll take the cube roots of both sides. When I take the cube roots of both sides, this 64 turns into a 4. And these guys go away. Oops. And that gets my bound, right? So now q is less than or equal to 4 times this quantity plus a size of L, and that's less than or equal to the advertised thing I was shooting for. So that's the proof. So I mean, we seem to be a long way off of sum sets and product sets at the moment. Sort of what we've done is sort of prove this important and lovely little lemma called the crossing lemma from graph theory, and we've used that to get this this meaningful theorem due to Semeretti and Trotter, which tells you the maximum number of pairwise incidences between a set of points and lines in the plane. Now we're gonna somehow, by magic, use the Semeretti-Trotter theorem to get this theorem of Alekesh. Yeah.
Sorry, this is a different topic, but how tight is that bound? Do you know?
It's certainly tied up to the constant. I mean, yeah.
I don't think anybody is trying to get that constant.
Okay.
Right. You can try. You can maybe improve it a little bit, but it's not something they're hoping to get the right order. The order is tight. Okay.
Yeah. So there's some. I have no. I don't know what it is.
It's a type of grid.
Okay.
All the constructions are various types of grids.
Okay. But it's not actually the standard grid, right? It's like a weirder one.
It's like depends what the size of E and L is, but like
oh,
n
okay.
times and 3/2 or something like that.
Okay, yeah. Okay. Anyway, so now we're gonna just we're just gonna sort of follow this very clever line of Elekesh to deduce that sum product bound from this set of points and lines. So so now I'm proving Elekesh's theorem. So I'm going to let A be any subset of the reals. And I'm going to construct a set of points and a set of lines in the plane from these things. So V is going to be the set A plus A Cartesian product A times A. So I'm sure you know what I mean by this, right? So I'm taking the set of ordered pairs where the first coordinate is something in the A plus A subset, and the second coordinate is something in the A times A product set. Now for every, so this, so it's this is just some grid in my plane, right? So I've got, we can, so I've got A plus A sort of sits on the x-axis, and A times A sits here, and every time you've got so we get some, funny kind of grid-like grid-like point set here. And now there are some nice lines that we'll see that hits lots of points. So for every say A and B in my set A, let little l sub AB be the line given by the equation y equals, let's say, A times x minus b. and declare capital L to be the set of all those little l sub ABs. Right. So now this line, I claim it contains lots of the points in my set V. So in fact, for every point C in my set, if you look at C plus A, well, C plus A is something in, or sorry, C plus B. Look at C plus B. C plus B is something in the sum set. But when you feed C plus B in as the x value here, out comes A times C, which is in the product set. So for every C in A, the point C plus B comma A times C is in V. Right, so every one of my lines is hitting a whole lot of points, one for each element of A. Okay, so right, so well, basically, this is the magic. Somehow this set that we've constructed, this A plus A and A times A, it's a grid, but it's a grid that has lots of lines going through it that intersect many of the points. And this is now exactly the right setting to apply Semereti-Trotter. So let's do. So my number of lines is exactly a squared. Right? So a cubed is exactly size of a times size of L. But size of a times size of L, this is this is a lower bound on the number of point line incidences I have. Right? Because each line has at least size of a points. So this is at most, I'm just going to say this in words, the number of point line incidences between V and L. Right? Because every line had at least a of these guys. And the Semereti-Trotter theorem has given us an upper bound on that maximum number of point line incidences. Namely, it's at most 4 times the number of points to the 2/3 times the number of lines to the 2/3 plus the number of points plus the number of lines. And now I just need to expand some things and figure out what some things are. So what is this? 4 times, so I'm going to leave V sitting there. The number of lines, that's the size of A squared. So this is size of A to the 4/3. Now, okay, I want to claim that we can get to this inequality here. And really, I want to claim something stronger. I want to claim that this first term is at least as large as the second or the third. Right? So if this term is at least as large as this one and at least as large as this one, then my inequality holds true. Right? So in other words, I want to claim that size of V to the 2/3 size of A to the 2/3 is at least the size of V, where that's just equivalent to saying, oh, sorry, this was 4/3. Size of V to the 2/3, size of A to the 4/3 is at least V. That's the same as saying this. Size of A to the 4/3 is at least size of V to the 1/3, so, well, that's this. So size of A to the 4th is at least V. Well, that's trivially true by this easy estimate, right? Size of A plus A and size of A times A, those are no more than size of A squared. So that holds true. And that means that this second term is dominated by the first. And the last term is even easier. So I claim that this one is at least as big as this. And that's the same as claiming size of V to the 2/3 is at least size of L. Oh, sorry, I should have gone down here. Yeah, sorry, size of, yeah, I want to work down here. So I'm claiming this term is at least as big as this. So that's same claiming size of V to the 2/3 is at least size of A to the 2/3. And that's just saying the size of V is at least the size of A. And again, that's just automatic. This sum set is at least the size of A already. So that one's true. And that means that this first term is at least as large as the second or the third, and that gets me this. And I'm just going to throw away 4 more because it makes the numbers come out a little bit better. So now, now I'm just going to erase and rearrange. But but we're done. So the size of A plus A times the size of A times A, this is exactly equal to the size of v, right? And what we've got here, rearranging, so if so let me just rearrange. So it's rearranging the size of v to the 2/3 is at least 1/16 times the size of a to the 5/3. And now if I take the 3/2 power, I get size of v is at least 1/64 times size of a to the 5/2, and since size of v is exactly what I'm trying to bound, that completes the proof. Right, so this was the bound I was aiming for. The number of points in my point set v should be at least 1/64 size of a to the 5/2, and yeah, and that's exactly what's dropped out just out of the crossing lemma. So yeah, there's somehow a lot of things in here that are a little bit sneaky. But this is really this type of crossing lemma is really the thing that's generated much of our understanding of these kinds of problems. And anyway, so this is a sample. This is not the best, but it's very elegant, and so that's, I think, what I want to stop with for the first half. So let's take a 10-minute break, and when we come back, I'm going to jump to a totally different topic, and we'll do that one.